Greetings and welcome to this edition of Teaching Difficult Concepts with Electude. Today we're going to be discussing diagnosing CAN bus networks. So in Electude, we have a number of great lessons that's going to walk the student through how the CAN bus network is constructed, from transmission lines, topology, configuration, protocol, arbitration, and error detection, even one here on diagnosis. But as a teacher, sometimes you want to give a practical example of how to do something on a real or live vehicle, and that's often very difficult to do. So what I'm going to focus on today is showing you how that can be done using the Electude simulator. So let's take a step back here and go into other modules. So I've got a CAN bus failure here all set up. And so as a teacher, you could do the same. You can select a CAN bus fault from the under the modules tab, or you can create one yourself using the DIY tool, and you could put this up project this on the board, have students follow along on their own devices. But what we got here is a car with that has a crank no start condition. So if we were to try to start this car up, we can see that the engine is cranking, but it is not starting. So what should we do here first? You might ask your students that question. The first thing we're going to do is grab the trusty diagnostic system, the scan tool, and see if we can communicate with this vehicle. As always, we'll always check for trouble codes. We see here communication not possible with the ECM or throttle valve control module, so we're not communicating with either of those devices. We can just go in here and just look and see if we can get some live data here. We'll just double confirm that. Yes, indeed, the key is on. Communication with ECM not possible. All right. So the scan tool is not going to do us any good from this point onward. But I will show you here in the information area block diagram. This is a nice illustrated view of the network system. So what we can access on this car is everything under the hood here. We can't go underneath the dash. We can go to the back of the car to access the fuel pump, but that's about it. So what's simulated in this is basically everything you see under the hood. So we're going to have access to this area here that I'm circling. We have access to ECM, the throttle valve control module, but we can't, even though we know it's there and we can measure this terminating resistor, we cannot go here. Neither can I go to this diagnostic connector. Typically on a real car, you would be able to access the CAN high and CAN low network from here, and you could take some measurements. But we're going to be using a breakout box to make similar measurements for that. But I did want to show you the configuration here. So here we have CAN high. Looks like it's a green wire with a white stripe. CAN low, solid green wire. Goes to the throttle valve control module, ECM. Here we have a 120 ohm terminating resistor. Here we have the other. They are connected in parallel with one another in this CAN bus network. So as you know, this might be a good point to bring up to your students. You know, you're always asking, why do I need to know Ohm's law? Well, here's a good Ohm's law problem for you. If you have 220 ohm resistors connected in parallel, what would the equivalent resistance be? So we're going to divide that number in half. So if we're making a measurement anywhere in this CAN bus network, we should measure roughly 60 ohms resistance if the network integrity is intact. So let's put this away for the moment. And let's get our breakout box out. Here's our breakout box, and we will be using a multimeter to measure CAN bus resistance. So as with any time that you're making a resistance measurement, you can't have any electricity flowing through the circuit, so we're going to turn the key off, but also we're going to disconnect the battery, because right now the computers are attempting to talk to one another. There is going to be voltage somewhere on those CAN lines, so we're going to unhook the battery. That's disabling all network communications. Now we can unplug the ECM that has the 120 ohm resistor in here. This wiring harness here goes to the other ECU that has that other 120 ohm terminating resistor. So we're going to connect that to our breakout box and connect this into the breakout box here. So essentially, this breakout box, you can almost think of it as almost like another module connected in parallel to all the other modules on the vehicle that's connected to that CAN bus network. If we open up our wiring diagram, let's take a peek at that. We'll make this nice and big for you to see. You might, as a teacher, you might even print this off and hand that to your class before you do an a lesson like this. And we can see here CAN high, CAN low. So anytime you're looking at a wiring diagram and you see these arrows, that's just basically it's showing you a page break. We're not showing you where these two items go, but you'd have to look up in another wiring diagram the other ends of these two. That's not a splice, that's just a page break. And somewhere else this wire would continue and go to other modules on the car. But in relationship to what we can test here today, we can access that CAN bus network goes to the throttle valve control module, pins 3 and 4. And then if we follow this here, pins 16 and 17, it does go elsewhere on the vehicle. Here again, another page break. It's just showing that those wires are going elsewhere. What's not shown here is that terminating resistor. There is that 120 ohm terminating resistor between these two terminals, which we saw in the block diagram. So we're going to be making our first measurement here at pins 16 and 17. And so we're going to close that. Here's 16 and 17. So the numbers here on this breakout box match the numbers on the wiring diagram. So we've got our battery disconnected. Let's go ahead and make our measurements here. So we're going to put this across 16 and 17. And we should measure 60 ohms if all is good here between these two. And looks like we got 120 ohms. So that means that we're only measuring one of the two resistors. So it looks like we probably have an open circuit somewhere between this control module and the other. But at this point, we don't know where the open is. It could be an open here inside this computer, and we're measuring the 120 ohm resistor on the other in the gateway computer. So what we're going to do is to eliminate this, we're going to start unplugging modules till we see this number change. So let's unhook this one first. As you can see, the number stayed 120. So what's connected at this point? We disconnected the entire car except for this computer. So we know that at least that 120 ohm resistor is good inside this computer, which is a very expensive computer, by the way, so it doesn't look like we need to replace that. So let's connect that back up, and let's disconnect this. Now, if this goes to overload, then we know we have an open circuit somewhere down the line here. So, and indeed, once it goes to overload, we'll move this to the next setting here, and you can see it is an open circuit. So we've got an open circuit somewhere in the CAN bus system, but we do not know exactly where at this point, or is it in the CAN high or the CAN low wire. So what we're going to do, our next step would be to put our multimeter away, and we are going to do some testing with an oscilloscope on a live circuit here. So what we're going to need to do, zoom out here just a bit, and we're going to reconnect this battery. And now we're going to get our trusty lab scope out, our 2-channel scope. As always, the negative lead needs to be connected to the battery negative. Turn our scope on, and we need 2 channels for this, one to measure CAN high and the other to measure CAN low. So let's go ahead and turn on channel 2. All right, we're at a 1 volt per division. That's good. Now, one thing that I think is, well, we'll wait here. Let's go ahead and. I was about ready to make a point, but it'll be more dramatic here in just a second. So let's zoom in on here. Now, to help students kind of help them distinguish between can high and can low, I kind of use a coloring system here. So the ocean is low on the horizon. The ocean water is blue. So we're going to say that the blue lead here is can low. So move this over to pin 16 is can low. And the sun is high in the sky, high on the horizon, so this is our can high. And initially here, we'll zoom in on this signal just a little bit. Initially here, you might say to yourself, oh, look, we got signals, we got can high and can low. Or do we? So there's 3 voltages that students need to kind of keep in their memory banks when we're discussing CAN bus. So the rest voltage, when no communication is taking place, rest voltage is at 2.5 volts. When transmitting a data, CAN low goes to 1.5 and CAN high goes to 3.5. And there should be a 2 volt differential between can high and can low to be able to send a message. So we could do some counting here and stuff, but to make this easy, I recommend that you put the channel 1 and channel 2 ground planes on at the same level. So we're going to move channel 2 up to the level of channel 1. So we already got channel 2 selected here. I'm just going to move that line up. And let's see if we indeed have 2 separate signals here, or if it's the same signal being ghosted. And if we look here, we've only got 1 signal here. We're getting a ghost image because there's still a connection between the two through this parallel connection. We're getting a ghosting of one of the 2 signals on the other. So which one? Let's just pause this for a moment and let's start doing some counting here. So because we were set at 1 volt per division, so there's 1 volt, 1.5, 2, 2.5. So here's our rest voltage, and then can high should be up here in the 3.5 volt area. So we're getting our can low, but no can high. So somewhere in this in the system here, we have an open in the CAN bus high circuit. So that's why I think it's really important to line up your 0 lines so you can more easily distinguish which one of the 2 signals are you missing if there's an open. And you're going to encounter open circuits more often than short circuits, just due to most faults, the wires will be broken or something like that. All those shorts can happen too. This particular fault is an open. All right, let's see where else on the car can we make a measurement to see whether or not we have any communications. Let's get that wiring diagram open again. And of course, we could make a measurement if we could gain access to the other control module or the assembly line communication data link connector. We could make a measurement there. But on the simulator, our choices are somewhat limited, but we can gain access to can high, can low here at the throttle valve control module. So let's just go down there. That's pin 3 and 4. We'll go down here and see what we have. So here's a twisted pair. Here's our communication lines coming in. There's can high, can low. And let's keep things consistent here. Put the red on can high and the blue on can low. Unfreeze our lab scope here. And as you can see here, if I freeze it, we do have a communication appears to be going on here. So if we look at our voltages, there's 1, 2, 2.5, 3, 3.5. And if we if we count the difference between can high and can low, there's a 2 volt differential, and a message can be sent. So the computers are looking for that 2 volt differential, and of course the computers can decipher this code and make sense of that. So we do have a signal here. That means we've got an open circuit somewhere between the control the throttle valve control module and the ECU. So in reality, we'd probably start, unwrapping the harness here, looking for, a loose or a loose connection, or maybe we'd start pulling on wires to see if one bends a little bit or stretches. But somewhere there's a break between here and here, somewhere in this wiring loom here. If we're to open up, so okay, if we get the wiring diagram out, so we were getting a signal here. That means somewhere between terminal 3 and 17 we have an open circuit. So what we're going to do is just simply replace this wire on the wiring diagram here. So we just strung a new wire on the car. We could say that we found the open circuit there in the harness somewhere. And now we need to verify our repair. So, of course, if the engine starts, we'll know that we've done some good. Of course, it is running now. That's a good sign, obviously. We'll unfreeze this, and you can see we've got communication here as before. But now let's go ahead and check this at the breakout box. So can high was 17, can low was 16. And you can see now we've got a signal there, can high, can low. So it's really easy to see that voltage differential when you superimpose your zero line. So that's probably the number one thing I want to stress, when you're hooking up a lab scope, to line up your zero lines. We can also now show you the terminating resistance. Will be the normal 60 ohm here. So I'm just going to shut the key off. Disconnect our battery. Can't have any communications going on here. We'll pull our meter out. And between 16 and 17, if all is well, we should read how much resistance? We should see 60 ohms. And 59.9, there we go, roughly 60 ohms. If I disconnect this connector, it should go to 120. So there's a terminating resistor in the gateway computer. And if I plug that back in and disconnect this, there's the 120 ohms inside the ECM. Plug them back together. There we go, back to 60. This is what you should see if measuring CAN bus terminating resistors. So that kind of wraps it up for today's little webinar. Hopefully this gives you just a couple ideas of maybe how you can use the engine simulator to demonstrate CAN bus, whether it's measuring the terminating resistors or using the lab scope. So fun little activity. I think you could make a good use of that in your class. So thanks for sharing this time with me today. And we'll be seeing you soon with another installment.